What do you think? Should we start it up?
Yeah, I think so.
Okay. Well, thank you all for virtually coming. Lucas is in the lab right there. I'm in the next room over, but that's the closest we could come to being in the same place for this. It's my honor to introduce Lucas here for his defense. I'm very, very proud that this day has come. I'm very sad that he'll be leaving. You have to know that, so let's see, Lucas had a bit of a checkered past. He came to MIT as an economist. We had to save him and bring him to robotics, and thank goodness for that, because he's just absolutely lit us up over the last few years. He came to our group right when we were in the DARPA Robotics Challenge and promised to show some of the videos from that. There's a great one of him jumping on the back of the Polaris trying to knock the robot over. And actually the first project he worked on with that was trying to get Atlas to get back up when it falls down, right? So Atlas is a almost 400-pound humanoid robot, and we were terrified that in this competition the robot would fall down and it would just be game over. So that was Lucas's project. It was like, okay, robot falls over, let's have a plan so it can get back up. Long story short, it's a 400-pound robot with like a 300-pound backpack and the kinematic reachability. Long story short, if you fall down, that robot never is getting back up. It's, until they have Atlas, the new Atlas can get back up in dramatic fashion, but ours never did. But Lucas went on to do work on the balancing control, and like I said, you'll see him and Andres jumping on the back of the Polaris and trying to knock the robot over. He did an amazing job as a part of the DARPA Robotics Challenge team. When we got a Valkyrie robot here, Lucas took over and got the control that we had running from Atlas working on Valkyrie in like a ridiculously small amount of time. It was incredibly impressive work. So he's always been extremely solid in the dynamics and control side of things. But then we started thinking more about manipulation. Lucas started thinking more about manipulation. And as much as we like the dynamics and control side of things, you can't do manipulation without thinking a lot and thinking deeply about perception. And Lucas, with some great collaborations with Pete and other people in the lab, really helped this lab learn how to do perception and think. And Lucas and Pete and others really thought really deeply about what does it mean to do perception so that you can do interesting dynamics and control with a manipulation robot. And that journey has just been so fun to watch and so great to be a part of. And I think that the series of results that he's going to tell you about today, including some that I think none of you have really seen yet, that are hot off the presses. He just got back into lab to do the last few experiments. They're just a fantastic body of work. So this is probably our last week in lab together, and I'm very sad for that, but I just can't wait to see what he comes up with after this. Lucas, please take the stage.
All right, thanks, Russ. So I hope everyone can hear me okay. Yeah, so thanks for that great introduction. So today I'm going to talk about robot manipulation with learned representations, and I'll try to give sort of an overview of what I've done during my PhD and how it all fits together. So, okay, so a little bit about me. So I'm a PhD student in the robot locomotion group here at MIT. And as Russ mentioned, my research has been mostly in robotic manipulation, sort of at the intersection of perception, control, and machine learning. So that involves getting robots to do non-trivial manipulation tasks like picking up a mug and hanging it on a rack by the handle, let's say. But as Russ mentioned, I previously worked on the MIT DARPA Robotics Challenge team doing planning and control for walking robots. So this is Andres and I testing out the balancing controller for this whole getting out of the car sequence, which was comical given how large the robot is and sort of how small the car is. And I had a lot of great times and learned a ton on this. And this was around 4 in the morning, I think, right before we sent the robot to California. And I think Russ actually was the one filming this video. So I still have a soft spot in my heart for walking robots. Okay, so here's just a few of the projects that I'm going to talk about today. So I'm going to try to talk about these 4 projects that sort of make up the core of the body of work for the PhD. Oh, one just public service announcement on how questions are going to work. So I think it's best to hold off on questions till the end. If you want to like unmute yourself and ask questions, we can do that at the end. And in the meantime, if you throw a question up in the chat, I'll try to look up there occasionally and answer them. Okay, so if we, just to set the stage a little bit for what I mean by manipulation, here are some examples. So here's Spot doing this cleaning up the kitchen task. On the top right, this is actually one of my favorite robot videos. This is from Willow Garage, the PR1, which is the predecessor to the PR2, doing this amazing job cleaning up this living room. The caveat being that this is teleopt. And then on the bottom, you have some examples of humans doing manipulation tasks like making sushi and cutting an avocado and spreading it on top. So this is the kind of things that we should keep in mind when we're thinking about manipulation. You know, the goal is that we want robots to be able to accomplish useful manipulation tasks like in the wild. So what I mean by that is without the aid of some, you know, highly instrumented or external motion capture system or fixtures or things of that nature. So, you know, you might ask the robot to do something with objects that maybe it's never seen before. So, you know, I'm a roboticist, so I like to try to formulate this in the language of robotics and sort of optimal control. So with a little bit of abusive notation, because I'm using X for state, and really we have to work from observations, we can try to write down this problem as an optimal control problem. So you want to minimize or find some policy pi that maps from states to actions to minimize some expected cost, maybe subject to some dynamics constraints. And I think this is pretty familiar to anyone who's in the robotics field. But I think manipulation presents some fundamental differences and challenges from other areas of robotics. And I think there's at least three. So the first is that it's not clear what the state space should be. So, and when I say that, I mean especially the state space of the world rather than the state space of the robot. So for the robot, you know, we can have an IMU, we can have encoders, we can know what our state is, but what's the state of that shoe or the rope that's on the table? That's a much more nebulous question. Secondly, what's the cost function? So, you know, for robotics, we love having, you know, let's say a quadratic trajectory tracking cost for something like LQR. But if I ask your robot to, you know, clean up the kitchen, it's not at all obvious that a trajectory tracking cost is going to allow us to do that. And then lastly, you know, it's not obvious what the dynamics function is. So again, when I say the dynamics function, I mean the dynamics of the world rather than the dynamics of the robot. So even though Atlas is a very complicated robot, it is well modeled by sort of Lagrangian mechanics. Whereas if I ask you, if you grabbed that rope and pulled it, what will happen? That's actually much harder to answer. So that sort of naturally led into the three questions that kind of I try to answer in the thesis, which are, you know, what's the right state space or object representation for doing manipulation? Secondly, how can you communicate task objectives to the robot, especially in the case where you have to manipulate novel object instances? And then lastly, how can you enable robots to actually get to doing closed loop feedback control for manipulation? So these are kind of the three questions that will underpin the talk, and I'll try to show how each project connects back to these. So the first project I want to talk about is dense object nets. And this is really tackling the first question, which is what's the appropriate state space or object representation? So what is it? This is joint work with Pete Florence, by the way. So it's a dense visual representation that's going to be useful for a variety of manipulation tasks. It's not going to rely on having 3D object meshes or poses, and it's going to be able to be learned self-supervised. And the reasons that we wanted to do this project were we wanted a rich visual representation for doing manipulation beyond what I call the pick and drop task, and I'll explain what that is in a second here. And also we wanted to get away from using, you know, object meshes and relying on pre-built templates. And we also wanted to be able to handle deformable objects to some extent. So I think if we're going to talk about manipulation, we should think about tasks. And I think there's at least two axes to think about tasks on. So one is sort of how complex the task is, and the other is how general is your solution. So sort of the simplest task you can imagine is the task of just pick up anything. And there's been really good work here and the solutions are very general in the sense that they can pick up, any object you might put in front of the robot. Sort of going down the list of complexity, you have this sort of spot cleaning up the kitchen task. But I would venture to say that this maybe isn't the most general solution. If you actually look really carefully down here, you'll see an April tag that the robot's using to localize. So now I want to talk a little bit about this pick up a specific object task. And this is basically what the Amazon Robotics Challenge was. So you'll see a lot of this in industry now, which is robots doing these bin picking tasks. And the Amazon Robotics Challenge was essentially this task, where additionally you maybe had to pick a specific object rather than just any object from the pile. So how did teams actually solve the Amazon Robotics Challenge? So I think most teams ended up with a solution that looked like combining a grasp success model, which just means, if I were to put my gripper or suction cup here and execute my grasp or suction, would I actually manage to pick something up? And they combine that with a visual representation, which is just instance segmentation, which is just which pixels correspond to which object. And so I think most teams, basically, their solutions were a combination of these two things. And there's been a lot of good work on both sides of this problem. So to set the stage a little bit, I want to talk about sort of what the perceptual representations are in computer vision and how they relate to robotic manipulation. So there was sort of a revolution in computer vision in 2012 with deep learning and big data sets like ImageNet. And the representations started simple, like classifying the whole image like ImageNet, through detection up through instance segmentation, where you get a per pixel annotation of what each object is. And that's essentially the representation that was used in the Amazon Robotics Challenge. So if you want to do tasks like this that just involve grabbing something and putting it somewhere else, just dropping it, then this instance segmentation representation is sufficient. But now if you want to do a more complex task that's a little bit of more of a purposeful manipulation, you actually want to grab something and do something beyond just dropping it, well, you're going to need to know more than just the pixels corresponding to that object. You need to know something about the structure. And so there's been other things happening in the computer vision world, both sort of sparse key point detection and also these dense pose approaches. And the work that we're going to do is very related to these two. And actually, this mug on rack example will actually be the next project, and that will use a sparse key point representation. So coming back to sort of this task hierarchy, dense object nets, which is this current project, it's going to do a task that's a little bit more than just pick and drop. We actually want to grasp the object by a specific point, let's say. And this is sort of just an example task to show off the object representation. And then later, we'll show what else you can do with that object representation. And we set ourselves a couple goals for this project. We wanted it to work for deformable objects, and we would also like it to be self-supervised. Okay, so what can you actually do? Just a preview of the results. You can go down and click on a point on the object and actually identify that point with your camera and go ahead and pick it up. And you can even do that at the category level. Okay, so the starting point is really this paper from Tanner Schmidt and Dieter Fox, where they were learning sort of these dense visual descriptors in the context of a human pose estimation task. So I want to spend a little bit of time on this slide, sort of just explaining what dense descriptors are. So I think of dense descriptors as essentially providing like a coordinate system for the object. Okay, so what we're going to do is we're going to take an input image, which is W by H by 3, and we're going to map it to what we call a descriptor image, which is W by H by D. And D here is a hyperparameter, it's a choice. So typically we use D equals 3. And we want these descriptors to have specific properties. In particular, we want that the descriptor corresponding to a point on the object, let's say the tail of the caterpillar, that point should be unique and distinct from the descriptor corresponding to a different point on the object, like the ear. And also we want that they're invariant under, let's say, changing camera positions, lighting, deformation. So, the address of the tail, it doesn't change if I rotate the caterpillar around. So that's really what allows me to solve the correspondence problem. So if I choose D to be equal to 3, then I can actually map that vector onto the RGB color space, and you'll get these really nice visualizations. And what you should see is that different points on the object have different colors, unique, and also that, I'll later play a video of this, that the color corresponding to a point on the object, which corresponds to the descriptor for that point, it doesn't change if I rotate the object. So the color of the tail should always stay the same here. Okay, so how are we going to get such a representation? Well, we're going to use deep learning. And to train it, we're going to use something called a pixel-wise contrastive loss. So given a pair of images for which we know correspondence, and I'll explain how we get these in a second, but we know that this pixel here in the left image, which is on the right leg of this caterpillar, is actually the same point here in the right image. So if you think about what we asked our representation to do, the descriptors corresponding to these two pixels should actually be the same, okay? So we're gonna have what we call the match loss, which pushes those two vectors together. And that's sort of half the battle. If we only had that, we could sort of trivially map every point to the origin, and we would have trivially minimized this loss function. So we also need to ensure that points that are corresponding to different points get mapped to different points in this embedding space. So the head of the caterpillar is not the background, so the descriptor corresponding to this pixel and this pixel should be different. And this non-match loss is just asking them to be a certain margin apart. And then the total loss is a combination of these two. Okay, so whenever you think about doing sort of machine learning, you have to think about where does your data come from? So how do we actually get these pairs of images? So what we're gonna do is we have a robot with a camera mounted on the end effector. We can move that camera around to get many different views of a scene. And then because we've calibrated this camera and we know how to do forward kinematics, we actually know the relative transform between the cameras. And then we can back project points. So in practice, what this means is I can take a point on the object, let's say the right leg here, and because I know where the cameras were, I can back project, and that's exactly telling me that this pixel is the same object point as that pixel. And so this is how we get the supervision for our method. It's really multi-view consistency, and it's completely self-supervised, so we never had to label anything. So here's just a picture of what our robot setup looked like at the time. We had these sort of very homemade rubber band fingers, which we've since improved, and you can see the camera mounted here on the wrist. And so this is what that process actually looks like. We go and make a scan, and then we know where all those relative camera poses are and can do that projection. Okay, so there was a few sort of technical points that were needed to make this work well, and I'm gonna go fairly quickly over these and focus sort of on the big picture, but I encourage you to ask questions at the end or go read the thesis if you want more details. So it's important to sort of focus the representational power of the model on the object by doing some clever masking. You also need to domain randomize the background, so you learn a coordinate system that's really unique to the object and not relative to the background. And then you also need to sort of appropriately scale this loss function. So this is, so what do the results actually look like here? So here we're visualizing a three-dimensional descriptor image again. So D is 3, and we're projecting it onto the color space. And what you should see, this is Pete holding our caterpillar object. What you should see is that as we move this around, the colors corresponding to, let's say, the tail or the ear, they stay the same independent of, lighting and deformation. And every frame is being processed independently here. We're not doing any tracking. And we can run this sort of at 20 hertz, which is roughly real time. Okay, so fundamentally, what all this has done is allow us to solve the correspondence problem. So on the left here, you'll see a reference image and a green reticle here in the bottom. And when I play this video, you'll see me moving that reticle around with my mouse. And then the goal is to find the corresponding pixel. So if I highlight, let's say, the right ear in the left image, I want to find the right ear in the right image. And so the center image and the right image are actually the same. You'll see the red reticle down here in the right image track the correspondence, and then the heat map just shows you sort of the distances in the descriptor space. So I can highlight the right ear, go to the left ear, and actually this is dense, so I can move all the way down the object and find correspondences. So at its core, this is what those descriptor vectors are used for. They're fundamentally about finding correspondences across images or scenes. Okay, so I don't have time to get into the quantitative results, but we did lots of analysis, and our approach offers significant improvements over baselines, and I encourage you to read the paper if you want to see more. So what can you do with this in terms of actually using this for manipulation? So you can go in a single image, click a reference point, you store that descriptor, and now you can put that object down in front of the robot, and you can always go pick it up by that point. And you can do this in spite of changing object pose and even deformations in this case. And here we're showing that you can do the right ear versus the left ear. And this is interesting because if you're using like a patch-based descriptor, the right and left ears look very similar, but the receptive field of the network here is large, and you can actually go and do this. Okay, so we noticed throughout the training process that descriptors sort of seem to naturally overlap across different objects. So this led us to ask the question, what happens if we train on different instances of the same like class or category? So here are a bunch of different hats. Let's say we run our model trained on all these different hats. Now notice that because our method just uses multi-view consistency as a source of supervision, there's nothing in the data that connects, let's say, this MIT hat in the bottom left corner to the Princeton hat in the center. But sort of magically, what ends up happening is that you get actually very consistent colorings, embeddings in the descriptor space across the category, even though there's no supervision. So this was sort of a pleasant surprise. So what can we actually do in terms of manipulation? We can do the similar to the caterpillar, where we go and click on a single point, here the tongue of the shoe, and then we can actually pick up objects by that point, but not just one object, lots of different objects from the category. So these are all shoes from the training set. Again, there's no cross shoe labels, but here are some previously unseen shoes, and it actually generalizes quite well. And here, I was actually standing behind the camera and threw my shoe on there, and it still works. So just to summarize, what is a dense descriptor representation? It works for sort of any 3D reconstructible object. It's pretty sample efficient. Also, the output, which is fundamentally solving correspondence, it's pretty interpretable, and that allows it to be used as an input to a variety of other systems. So you're going to see 2 other projects in this thesis that use this representation. And the nice thing is that we sort of take advantage of the structure and existing algorithms that we know, like calibration, 3D reconstruction, IK, and grass planning, and we really focus on learning the hard part, which is the perceptual model in this case. Okay, so the next project I want to talk about is KPAM. And coming back to those thesis questions, this is really going to be tackling the first 2. So what is sort of the right way to represent objects, but also how can you communicate task objectives to the robot? Okay, so this is joint work with Pete and Wei. So what is it? It's a framework and algorithm for tackling category level manipulation tasks. And what I mean by that is the task you have to do with many different instances of the category. So here you see me doing this mug task, but for lots of different mugs. It's also a category level object representation that can handle the large intra-class shape, topology, and texture variations. And the reason that we embarked on this project was that we felt like existing object representations couldn't quite capture what was needed for doing these category level tasks. And the dense descriptors, they show pretty good category level generalization, but they weren't quite the right fit for this project. Okay, so if you recall dense object nets, it was doing this pretty simple task of grabbing an object by a specific point, which in and of itself is not necessarily a useful manipulation task. So now KPAM is going to be doing a task that's like one step more complex, which is putting objects from a category into a specific configuration. So we want to be able to do things like this. So grab a mug and then hang it on the rack by the handle, okay? And we want an approach that can do this not just for this one mug, but actually we want to do it for all these different mugs. And every object you'll see in this section has never been seen before by the robot. And so we want one approach that can handle actually all the different size, shape, texture, and topology variations that you get within a category. So sort of more formally, the problem statement is that you want to manipulate potentially unknown rigid objects from a category like mugs or shoes, into desired target configurations. So if we think about the different steps of the problem, we first need to grasp the object. And actually, we think that there's pretty good solutions out there for this. So you can either use sort of a classical geometric-based solution for this or deep learning, but we don't think that grasping the object is the main sort of difficulty. Once you've grasped the object, it's actually pretty simple to move it. If you have a good grasp, it's basically rigidly attached to your end effector, so actually moving the object isn't the challenge either. So the challenge is really deciding where you want to put the object, and that's what we're going to focus on. So pose-based approaches have, had a lot of success in manipulation in the past, and I think they can work really well when you're dealing with a single known object. But I think there's at least two challenges to using pose-based approaches for these category level tasks. So first is that it's not really necessarily well defined across different instances of a category. So if I show you a sneaker, which is an instance of the shoe category, well, I can also show you a high heel or like a boot. So if you have to define the pose that's consistent across all of those, it's not clear how to do it. Additionally, there's a lot of ambiguity. So I could put the origin of the frame at the heel, at the sole, at the tongue, or the toe. For a single object, those are actually all equivalent, but they have very different implications if you propagate them to the other instances of this category. And additionally, it can be pretty difficult to specify tasks using pose-based targets exactly because of this ambiguity. So to give a little sort of simple cartoon example of that, here's like a cartoon of putting the mug on the rack. So I have this mug here in the top left. If I actually just take that mug and shrink it down, then it turns out that pose is actually totally well defined. But if I just put the shrunk mug at the position of the big mug, we obviously aren't accomplishing the task, because the task is not about pose, it's really about having the handle around the rack. So pose targets, they can be physically infeasible, or they can just fail to accomplish the task. And this really arises because there's intra-category shape variation. So how do you define the target pose for all instances of a category? So for any one instance, it's just an SE3 transform, but it's going to be different for every different instance because they have different geometry. So in our view, this means that SE3 pose is not very meaningful in the context of category level manipulation tasks. So what we're going to do instead is, instead of using pose, we're going to use semantic 3D key points as the object representation. And then we're going to use an optimization program that allows you to put costs and constraints on these key points as the task specification mechanism. And this sort of goes nicely with the fact that key point detection has really matured in the computer vision literature, and you can actually detect these from RGBD images, for example. Okay, so to give you a little sort of example, here's a toy example of putting mugs upright on a table. So instead of representing the object by a pose, we're actually going to represent it by two key points. So let's say the bottom center and the top center. And then we're going to represent the action. Because we're going to rigidly grasp this object, we can move it however we want. So the action is just going to be an SE3 transform that moves the key points. So if I want to specify the task of putting the mug upright at a specific location, how would I do that? So what we're going to do is we're going to say, well, it's an optimization program. You get to optimize over the action you're going to take. And you can put costs and constraints on how the key points are going to move. So in this example, you could put a constraint that the red key point is at the target location, and a cost saying that the mug axis is aligned with the vertical. And if you do that, that's actually going to be a pretty good way to specify a lot of pick and place tasks at the category level. So if you recall, in our cartoon example, here's what happens if you do pose-based transfer. But if you just put a constraint that the handle center key point is on the rack and some costs about where the other key points are, you can actually get really nice transfer for different instances of the category using this key point-based approach. And I want to emphasize that these key points are really in 3D and not in 2D. And that's important. The real world is in 3D. So if you want to do optimization over an SE3 transform, which is what your robot can actually do, you need your representation to be in 3D as well. So how does the actual full pipeline work? So you start with the robot taking an RGBD image. We do instance segmentation. From that, we're going to run our 3D key point detection network, which is going to detect these 3D key points, and I'll talk more about that in a second. Then we're going to run our optimization program to figure out what action we actually want to apply. Then we can combine that with your favorite grasp planner to actually grasp the object and apply the action. And the nice thing about this pipeline is that it's very modular, and all the input and output is sort of very well defined, so you can mix and match. Like if you want to put in a different grasp planner, it's very easy to do that in this framework. So here's an example of us actually doing that task in practice. Okay, so how do we do key point detection? So we're going to detect 3D key points directly from RGBD images, and we're very much going to build on some advances from the computer vision literature. And one important difference is compared to dense object nets, which was completely self-supervised, here we're back in the world of supervised learning. So we're going to need a way to build our own labeled data set. So to build our labeled data set, we actually are going to borrow a trick from the previous approach, which is to label in 3D and back project those labels to 2D, because we know where the camera has moved. So here you can see me labeling this shoe in 3D. And we actually labeled a pretty small data set by computer vision standards, so only about 10 shoes and 20 mugs. And just to give you an idea, it only took us about 4 hours to generate this data set. So the key point detection network essentially outputs a probability distribution over where it thinks each key point is going to be. And then the way that we actually localize the key point is we take the expectation of that distribution. So an important thing to note here is because the key points are sparse and they're in 3D, we can actually do inference through occlusion. So even if this bottom heel key point is occluded, we can actually still detect it. So just to give you an idea of the experimental results, we did a large number of experiments on 3 different category level tasks. You've already seen 2 of them, hanging the mug on the rack, which is here at the bottom, and putting the mug on the shelf. And then we're going to do one more task involving shoes. And here on the left, you can see the key points that we chose for each object category. So for the mugs, we have 3 key points, the top, the bottom, and the handle. And for the shoes, we chose 6 key points that roughly capture the shape of the shoes. So here's this shoe on rack task where you need to grab the shoe and place it on the rack in this position with the toe facing away from the robot. So the really nice thing about this method is it can handle all the variation that you get in a category. So here's just a video of some of the shoes that we used in our experiments. So you've got everything from sneakers to soccer shoes to boots. And we even have some baby shoes in there that our mechanical engineer brought in. And so I spent several days running experiments on all these different shoes and trying to quantify the results. And you can get these really nice tiled videos showing all the shoes that we did our experiments on. So just to, I don't want to spend too much time on this slide because it's a little dense, and I encourage you to read the paper if you have more questions, but I sort of just want to draw your attention to the success rates on the task. So we do really well on the shoe task as well as on the mug on shelf task. And for the mug on rack task, for anything that you would consider like a regular size mug, we actually do really well. But it turns out we also had some really, really small sort of like kid-sized mugs in our data set whose handles are about 1 to 1.5 centimeters in diameter. So we can still do those about half the time, but it's definitely more challenging. And I'm happy to talk about that in the questions at the end. Okay, so I want to briefly just comment on key points as an object representation. So they're definitely a partial but task-specific representation of objects in a category. They're not everything. So you definitely still need object geometry for things like grasping and collision-free planning, but the semantic information is really coming from the key points. And their strength really comes from the fact that they ignore task-irrelevant details, which make them robust to shape, texture, and topology variation. And there's other ways that you could go about detecting key points other than using a neural network. But the nice thing about the neural network is that its performance is really only limited by its data set. So as an example of that, during the MIT visit days a few years ago, we actually were running this demo live and we were having the students put their shoes up here if they wanted to, and we would run it. And someone put a high heel up there, and we failed because there was no high heels in the data set. So we just went on Amazon, bought a few high heels, labeled them, retrained our network, and then we could do high heels. And these are different heels. These aren't the ones in the data set. So the nice thing is that there's a clear path to sort of repairing and improving the system if it fails. And that's sort of a nice thing that you get out of being in the supervised learning world again. Okay, so just to summarize, it's a novel formulation of the category level pick and place problem that represents objects as these semantic 3D key points. And then it's a task specification via an optimization program on these key points. We also developed a manipulation pipeline that lets you nicely factor the problem. And then we did extensive hardware experiments sort of demonstrating the effectiveness of the approach. So now I want to talk about this Visuomotor policy learning paper. So sort of trying to complete the story of the thesis. So far we've only thought about the first two questions. And in this project, we really try to answer all three. Okay, so this is joint work with Pete. And so what is this project? It's a factorization of Visuomotor policies that use dense object nets as the representation. And then it's using this factorization to perform efficient imitation learning. And the reason is because we wanted to get to closed loop feedback control policies for manipulation. So what I mean by that is in the first two projects, it was very much the case of the robot looks at the world, it does some processing, and then it closes its eyes and it just executes the policy open loop. And that led to some really comical failures, and we really wanted to get a policy that continuously looks at images and decides what to do. So we're going to try to do tasks like this. So these tasks, you can see the robot's actually reactive. We've got a task with a deformable object, a category level task, some non-prehensile manipulation. In the bottom right, you can see a task that really highlights the real-time feedback nature of the approach. Okay, so suppose you want to do a task like this. So pick up a hat in this case and hang it on a hat rack. How would you go about doing that? And you actually want a policy that goes from images to actions. So images are really high dimensional. So a typical VGA resolution image has like 640 by 480 by 3. And that's just too much for a policy to handle. So typically we use something to compress that image down to a low dimensional representation Z. We combine that with information from our robot, like our encoders. And then we run it through a fairly small policy model. This is typically just a few layers of MLP or LSTM to determine our action. And typically what's been done in the literature is to use something like an autoencoder and then to let Z be the latent code from the autoencoder. And there's been a lot of great work on this. So what we decided to do is actually replace the autoencoder with our dense correspondence model. So we think that for doing tasks like this, spatial information about the object is actually really, really valuable. So what we're going to do is we're going to select descriptors corresponding to points on the object. And because the dense descriptor network is fundamentally solving the correspondence problem, it's going to allow us to track these descriptors over time. So now what Z is going to be is it's going to be the location of these descriptors. And that location can either be in the pixel space or in the 3D space. So how are we going to train this? Well, if you think back to the original dense object nets paper, we had a static scene with a wrist-mounted camera that we would move around, and that's how we would get our supervision. So now the scenes are dynamic, so we can't really do that. So what we would do is we'd have multiple calibrated and time-synchronized external cameras, and then we can get correspondence via that source. So these are two images taken at the same time instant, and we know, for example, that this pixel here in the left image corresponds to that pixel there in the right image. And this is what allows us to train our dense object nets representation still in a self-supervised way. So to give you an idea of what the representation actually is, here on the left, if you think back to that original caterpillar example where I was mousing over and you saw these heat maps, this is the same thing, but now the right images are going to move. So on the left, I'm highlighting the point that I want to find in the right image. but I can actually do this through time now. So I can track this point through time and space, and even as the object moves around. So this is really what the input to the policy network is. And it's not just one key point, but we actually track a whole bunch of key points through time. So here we are tracking this set of reference key points over time. So these locations are really the input to our policy. So how do we go from this representation to an actual policy? Well, what we're going to do is we're going to train it using behavior cloning. So this basically just says, copy what the expert did, okay? So the demonstrations are going to be provided via human teleoping. So here's an example of Pete teleoping this shoe flip task. And what we're going to do is ask the network to just say, to copy what Pete did when it saw a similar image. Okay, so that's called behavior cloning. So what actual kinds of results can you get with this? So here we did about 50 demonstrations, which amounts to like about 15 minutes of demonstration time of us teleoping this task of pushing this box across the table to this red line. And now we can actually run this policy autonomously. So this robot is actually receiving commands at 5 hertz, and the images are actually coming from this camera right here. And you can see that it's actually pushing this object across to the table. And this might look similar to some of the previous things I've shown you. But now we can actually go and disturb this, okay? And the policy is very reactive, right? So it's actually doing real-time closed-loop feedback off the images. And this was a first for us, and we were excited. And you can actually get pretty high performance solution out of this. It's quite accurate, and it's not sort of a shaky robot like maybe you've seen in some other approaches. You can also do things like manipulate deformable objects. So here, grabbing a hat and hanging it on the rack. And you can do this even if the object is sort of changing position. And I think in the next one, Pete's going to hit the hat mid-go and will adjust. So if you think back to the original dense object nets paper, we actually showed that the descriptors generalized at the category level. So we could find correspondences across different instances of category. So here's that same heat map visualization, finding correspondences across a single shoe, but we can actually find correspondences across different shoes. So on the left is the boot, and on the right are sneakers. So now if we give demonstrations at a category level, and we combine that with our category level perception system, we can actually do some category level tasks. So we provided a bunch of demonstrations of flipping over different shoes, and now we can actually deploy a policy that works on all different shoe instances. So these are all shoes from the training set, but pretty soon here, we're going to start putting down previously unseen shoes, and the policy can still generalize, which was pretty exciting for us. And so it works not every time, so here's actually going to retry, but it works on a wide variety of shoes and shows some interesting behavior. So just to summarize, it's a novel formulation of the Visuomotor policy learning using self-supervised correspondence as the object representation. It's techniques for doing this multi-camera time-synchronized descriptor learning, and then it's sample-efficient imitation learning using this policy. And then we showed that this actually works on real hardware. So now I want to sort of get to the last project, which I think sort of nicely ties everything together. So again, similar to the previous project, this is going to be answering all 3 questions, but it's going to be doing it in a different way. What is it? It's basically going to use dense descriptors, but we're actually going to learn a dynamics model on how those key points are going to move. And then once we have a dynamics model, we can actually run closed loop feedback via model predictive control. So the reasons we want this is, again, we want to stay in the world of getting closed loop feedback control policies, but we don't want to rely on imitation learning. And there's a variety of reasons why, which I'll talk about. But once you have a model, you can do really powerful things like use it to do planning and achieve diverse goals. Okay, so just a brief preview of what the results look like. So using this approach, we can still do a task which is pretty similar to what you saw before. So stabilizing is pushing across the table. But now, if I want to do something else, like spin the box 180 degrees and then push it across the table, we can actually use our same approach to do that other task. And actually, we can use it to follow arbitrary trajectories. Okay, so the motivation is that the previous approach does get you to closed loop feedback control policies, but it relies on imitation learning. And imitation learning has a lot of nice features, but it also has some drawbacks. So we did 50 demonstrations just to learn a single task. We had to have expert demonstrations. Can't learn from off-policy data. And also somehow your performance can never be better than the demonstrator. So, in the current work, we want to be able to do that task of pushing across the table, okay? But we also want to be able to do the other tasks, which are, spinning and doing S-shaped trajectories and whatever you can come up with. And just to motivate why you really need closed loop feedback, here on the left is a closed loop rollout of this 180-degree spin, and on the right, I placed the box as close as I could to the initial condition and just ran the plan open loop, and you can see sort of how quickly it diverges. So you really do need closed loop feedback. Okay, so I want to come back to the slide that I sort of showed at the very beginning of the talk and show you how the different approaches fit in. So KPAM, it's representing objects via these semantic 3D key points, and then it's using an optimization program to basically say what the task is. So that's effectively the cost function in this equation. It's making a really simple assumption about the dynamics model, which is that you've rigidly grasped the object, and now it just moves together with your end effector. And once you've done that, you can actually get a policy by doing trajectory optimization with that model. Okay, but the problem is that that doesn't work for tasks where you're not rigidly grasping the object, okay, because this step breaks down. So the Visuomotor policy learning paper actually takes a really different approach. So it says, I'm not going to think about the cost function or the dynamics model. I'm directly going to jump to learning a policy that goes from images to actions. And the way it does that is via imitation learning. So it just basically has a bunch of supervision of X to U pairs, and it just copies it. So the current project, it's actually saying, well, let me actually learn a model of how these things move. Then if I want to push them to a specific point or a specific goal state, okay, I can actually do that by solving this optimization problem to get a policy. So that's how this last project sort of fits into the story of the thesis. So how do you learn a dynamics model? So you want to learn a dynamics model that looks like this. So xt plus 1 is f of xu. So x is state and u is action. Now the problem in the real world is that you don't have access to the underlying state. You get something like an observation, in this case an image. And of course you also get to access your robot state like join encoders, etc. So how should you represent the object state? Well, that's been a question that we've offered various solutions to throughout the thesis. So you could use pose, you could try to learn dynamics on the full image, you could use an autoencoder latent state, but what we're gonna do is use object key points. So similar to the Visuomotor policy learning paper, we're gonna try to track these points through time and space. And I really want you to think of these points, even though they're a 2D projection here, these points really are in 3D. And I'll try to show some 3D visualizations to drive that point home. And what we're trying to do is learn how are these points actually gonna move. So if the robot, let's say, moved to the right here, where are the key points gonna move? And that's represented by the purple here. So how are we gonna learn a dynamics model? Well, we're just gonna collect some training data of us interacting with the object, which is gonna be time series data of state action pairs. And what we wanna learn to do is predict how the key points are gonna move given a sequence of actions. So we're gonna parameterize our dynamics model as a function f with some parameters theta. And given the current state in action, we can predict the next state using this dynamics model. And actually by repeatedly applying it, we can actually predict arbitrarily far into the future. So then we're gonna actually train this to minimize the prediction error. So we wanna find parameters theta such that our predicted states actually map the states that actually occurred. So this is back in the world of supervised learning, but because you're using time series data, there's no like manual supervision needed. You just collect rollouts and that's enough to train your system. So in terms of the training data, you only need about 10 minutes of interaction data to learn the dynamics. You don't need expert demonstrations. Actually, any interactions are fine. You can use all data. You don't just need on-policy data. So previously, if you had a demonstration that failed, we would just throw that out. And also, it learns a global dynamics model that's valid everywhere. And then at the end, I'm going to show you how to use just a single demonstration to provide a trajectory that we're going to track. So if you compare this to the Visuomotor policy learning paper, we used 50 demonstrations, which amounted to about the same amount of time, 15 minutes. But those were all used to just learn this one task. If you now want to do some different trajectory, like spin 180 degrees, you'd have to go collect a whole new set of demonstrations. You can only use demonstrations that succeed, and that's in the sense in which it only uses on-policy data. Okay, so I said we're going to learn a dynamics model, so I'm going to try to show you sort of a visualization of what that actually looks like. So here in teal, or in like light blue, are the current detected key points. In dark blue is the dynamics model prediction of what it thinks is going to happen to those key points over time. And then in green is the ground truth of what actually happens. So I'll let this video play, and if the green and blue are sort of close or on top of each other, that means we've done a good job learning the dynamics. So you can see the model is not perfect, but it's sort of capturing the main dynamics. And if we couple that with high rate feedback, that's going to be enough to actually get good closed loop control. So how do I get from just having a dynamics model, which is this, to actually having a policy, which is what I want? So let's say that I'm initially here. This is my initial state, and I want to drive my system to this goal state. Well, what I want to do is I want to solve this optimization problem, find a sequence of actions that are going to drive me from the initial to the goal state. And then if I just execute the first action in that sequence and replan, that's going to be a model predictive controller. So there's a few caveats here. It's non-trivial to solve this planning problem, even if I give you a known model, okay? And that's because in this system, the dynamics are hybrid, they're nonlinear, which results in this being a non-convex optimization, okay? And in this case, F is actually a neural network for us, which makes things even harder. So currently what we do, but you are by no means restricted to doing this, is we use a gradient-free optimizer called model predictive path integral, which just happens to work well with the fact that we can roll out large number of samples in parallel because F is a neural network and we have it on a GPU. So to try to make this planning problem a little easier, we can do the following, which is to collect just a single demonstration, just to tell the system what we would like it to do. So here's a demonstration of me just teleoping the system from start to a goal. And all we're going to do is record the trajectory of those that the key points underwent. And now we can add those in as a trajectory running cost instead of just having a terminal cost. And this is a pretty, this is something that helps the optimization to converge. Just to show you sort of a 3D version of that, here's the 3D visualization of what that trajectory looks like. So every time you see an image like this, you should think of these 3D visualizations, because that's the underlying representation is actually 3D. Okay, so you've seen a lot of videos that have colors like this on it. So I'm going to try to step through and give you a sense of what each component is here. So in light blue is your current state. In green here, these green reticles are the goal state. And actually, you see this image on the right, it seems like it's a blend of two images. So it's a blend of the goal image and the current image, okay? The green lines are the demonstration trajectory that I just showed you. And then sort of the most interesting part is the purple, which is the predictions from the model of what it thinks is going to happen in terms of these key points under the optimized action sequence from our controller. And if this is working well, you should see that these predicted states track the demonstration and end up at the goal, and then the true states follow. So if I let the video play, there we go. So if I let the video play, that's exactly what happens, and you can sort of see what the MPC is doing along the way. And just to note, like all the videos you'll see are 1x unless it's noted otherwise. So the nice thing is that once you have a model, you can use it to track lots of different trajectories. So here are just 4 different trajectories that I thought up. So here we're spinning at 180 degrees, here pushing along different sides of the box, or doing this curved trajectory down here. And so the nice thing is you can reliably track these long horizon trajectories just from a single demonstration. So just to give you a sense of what this actually looks like from an off-board view, here's the robot tracking this 180-degree spin trajectory, and you can see sort of in the bottom right picture-in-picture of what the MPC algorithm is doing. So here's one where we're quite off from the initial plan, and here you can actually really clearly see the robot performing sort of real-time visual feedback. Again, it's feeding back off this camera right here. So this is an interesting one where the controller, it actually messes up the initial plan and ends up on the wrong side of the box. But about halfway through, it actually decides to switch contact modes and use the other side of the box to stabilize this plan and reach the goal. So just like before, we can be robust to external disturbances. So here I am with the poker annoying the robot. It was actually much harder to do this than in the previous project because I was in the lab by myself, and also this robot, this demo actually moves a lot faster than the previous one, so you need to be pretty quick from hitting enter to actually going and applying the disturbances. And we can also be robust to having visual clutter and objects in the background. Our vision model is pretty robust to that kind of thing. So just to show you that it's pretty reliable, here's doing one of those trajectories. This is the only video that's sped up, I think. It's sped up 10x just so we can get through these, but this is a single uncut video just to show you that we can actually do this pretty reliably. So it doesn't work. I want to caveat with saying, I think most demos you see, they don't work 100% of the time, and this is true with this one as well. So pushing is a little more challenging than it seems. It's hybrid, it's non-holonomic. So small distances in like L2 space can actually be pretty big in terms of the underlying dynamics. So it can be challenging to recover from perturbed initial conditions. And then, digging into our method a little bit, some of the causes of the failures are limitations of the MPC algorithm. So just because I've written down that MPC optimization problem doesn't mean that I can actually solve it every time. Sometimes we would have benefited from having a longer MPC horizon, and sometimes we ran into control limits. So just to show you 2 examples, here the robot similarly ends up on the wrong side of the box and gets it pretty close to the goal, so pushes all the way to the end. But here it would have needed to switch contact modes, and that's just hard from an optimization standpoint in this case. So as another example here, I started with quite a perturbed initial condition, and we would like to go further. You'll hear the robots click. And so what happened there is we ran into a kinematic singularity of the robot. So the algorithm in its current form doesn't have these built in. It wanted to go further towards the cameras, but the robot can't actually do that. So I think that all these things are solvable. They're not sort of fundamental limitations. The dynamics model is sort of agnostic to these problems. Okay, so to show you some quantitative results, here are 4 different trajectories. I encourage you to read the paper if you want to see more, but this is trying to give you a sense of how big the inlet funnels are. So this is the deviation of the initial condition from where the plan was. So for example, this point is 2 centimeters and 60 degrees off, and then a blue is a success, and a red is a failure. So it can handle quite a variety of initial conditions. All right, so just to summarize, it's a novel formulation of predictive model learning using learned dense visual descriptors. We did lots of experimental validation and real-world experiments. And if you go read the thesis, you can see some simulation experiments showing that it's got improved performance over a variety of baselines. So just to wrap up, I talked about 4 different projects: dense object nets, which is a way of solving the correspondence problem and representing objects; KPAM, which was the semantic 3D key points for doing these category level tasks; the Visuomotor policy learning, which really uses dense object nets in an imitation learning framework to get to closed loop feedback control; and then the final project, which really shows how to use the dense object nets representation to actually learn a dynamics model and get to closed loop control by doing model predictive control rather than imitation learn. So I see that there are a few questions, but maybe I will just go through my acknowledgements first, and then we'll open it up for questions. First I want to thank Russ for being a great advisor. He took a chance on me when I was still an econ PhD student, letting me be on the DRC team and later joining the lab. And initially I thought that all the PIs were like Russ, but over the years I've realized that that's not the case. He has both a great eye for the big picture, but also loves to get into the details of equations on the whiteboard. And he even still writes code, which I think is pretty unique. And on the academic side, he's really instilled in me the importance, of doing serious, rigorous work, and has always pushed me to hold myself to a high standard. And I really appreciate that. He's really guided me through the PhD, but also sort of allowed me the freedom to pursue my own ideas. So I just want to say a big thanks to Russ. I also want to thank my committee, Alberto and Phil, for giving me great feedback on my thesis and being really supportive throughout the process, which sort of was difficult at the end with the whole COVID situation. Alberto has really been a great mentor to me throughout the years, even before he was on my committee, and we had a lot of great chats. I also just want to thank all the other MIT faculty that I've interacted with over the years. I think I've gotten used to just running into you guys in the hall or at seminars and just being able to have great stimulating discussions. And now that I'm leaving MIT, I realize sort of what a privilege that's been. I also want to say thanks to Pete to being both a great friend and a co-author. He was really my main sort of partner in crime throughout the thesis, and we worked on a lot of projects together. So it was a pleasure to be able to work with someone who I can also call a friend, and it definitely made the PhD much more enjoyable. I want to say thanks to the DRC team. I learned a lot during my time with the team and also had a great time doing it. And I really want to say a special thanks to Pat and Andres, who spent a lot of hours answering my questions at the beginning in this tiny little office in N9, which this was the only picture I could find. And they really helped me to go from sort of knowing nothing about robotics to knowing something. I just want to thank the Robot Locomotion Group in general for being a great and intellectually stimulating place, and also my collaborators on the different projects over the years. I want to thank my friends for going on lots of great adventures and having a great time. There's too many of you to name, but I think you all know who you are, and hopefully you're up here in a picture somewhere. I want to thank my family, my mom, my dad, and my sister for always encouraging me and believing in me, even through periods that were sort of difficult and more uncertain. And I especially want to say thanks to my parents for spending so much time with me growing up and working hard to give me every opportunity to succeed. They've really shaped who I've become, both as a scholar and more importantly, as a person. And finally, I want to say thanks to my girlfriend, Katie, who's been a great sport, tolerating all my rants about robotics. And it's been great having a partner throughout the journey, a journey which isn't always the easiest. And you've definitely helped remind me that there's a life outside research, and all the great adventures we've had through the years have really helped me sort of keep a great balance. And so with that, I'm happy to open it up for questions. So maybe I will try to look at the chat, and or Russ, do you want to say how this is going to work?
Great. That was a great talk, Lucas. Thank you very much. Yeah, I think you all have the ability to unmute yourself. Chris and Ben sent in some great questions. So why don't you start with those, Lucas, and then.
Sure. So Chris had a question. I'll just repeat it. So is there some mechanism by which the Visuomotor policy retries in a different way after the failure, or is this implicit from the randomness of the disturbance caused by the prior failure? So actually, all the demonstrations had no retrying. They were actually just, so for the shoes, the one you're talking about, they actually just went and succeeded on the first try. But we were using an LSTM as our policy network, which actually has like internal state. And so it just turned out that if it missed and it got back here, which kind of looks like the initial state, after a while, the internal state of the LSTM will kind of reset back to the beginning and it will autonomously retry. So that was actually completely unexpected to us, and we didn't do anything special to do that. So Ben Birchfield asked, clarification on the key point estimate, do you use the mode or the center of mass in the heat map? It's the center of mass, so the expectation. So the reason we did that is because that is a nice, going from a distribution to its expectation is a differentiable operation versus something like taking the max. So that allows it to be trainable end to end. So, okay, Ben asked, when you use dense descriptors for Visuomotor policies, how do you select the low-dimensional set of reference points to use as input to the policy network? So good question. The answer is randomly. As long as you select random ones that are roughly separated on the object, that's sufficient. That captures enough information for doing the policy. For the key points work, for the key point dynamics work, it's a little bit different and much more subtle. So I don't have time to get into that now, but I encourage you to reach out to me or read the thesis for sort of the differences there. So Honkai asked, for the RL model, how robust is the dynamics? Is it easy to generalize the dynamics model with a slightly different geometry shape and dynamic parameters like mass and inertia? Good question. I think the answer is, I don't know yet. I think more work, we have to do more work to figure that out. I think key points are great because they're a sparse representation. When you're learning about dynamics, you do need, especially pushing or something like that, geometry really matters. So I think to really get a high performance solution in the future, we're gonna have to have some mix of sparse and dense representation. Eric asked, for the MPPI setup, do you have to explicitly encode anything for figuring out different contact modes? No. So even though all the results I showed you for that final key point dynamics approach were in that pushing example, there's actually nothing specific to that pushing example baked into the method anywhere. So the way that we learn dynamics is general, and the way that we do planning is general. So it's actually controlling the end effector velocity in that case. That's what U is. So it just figured out to go and do that and get on the other side of the box. So there was nothing sort of explicit there.
Awesome, thanks.
Andy Barry, can you explain a bit more about the integration of a robot state into the dynamics model? Do you have states for the contact point with respect to key points? So the way it works is the state is the key points in the 3D world, and then we also just want to know, like, where is our end effector? So we just have a point which is, or we say what the XYZ location of the end effector is. That's how the robot state gets put in. Does that make sense, Andy? So it's not in a relative frame.
Do you also have a state for if you are in contact or not?
No, because you don't. So yeah, I thought a lot about that. So the answer is no, because how would you actually know that?
Exactly, I was wondering.
So the answer is no. And the other thing is, when you have a dynamics model that you want to be able to run for multiple time steps into the future, anything you put in the state, you better be able to predict, right?
Yeah.
So there's things that you could put in like, oh, my contact sensor is firing, I'm in contact. But if you actually want to do prediction from I'm not in contact, what's going to happen 3 seconds into the future, you actually need to predict that. So no, it's not in there. It has to figure it out.
Got it. Okay, I actually have a second question now that I have you.
Right.
Can you wildly speculate about how far you are from folding laundry with this type of strategy? Like, say you had a t-shirt and you had key points. It seems like you're maybe not that far.
So I actually, yeah. So what I learned from the last project is I have hope for learning dynamics models. I actually think that that's possible. But there was one slide where I said, that doesn't mean just because you have a learned dynamics problem, like the battle is not won. Like solving the planning problem is still really hard. And I think people in robotics, we've always known that. It's not like planning became easy just because we're doing learning. So right now the planner is very simple. It's just basically like a fancy cross entropy method. But I think more work needs to be done to like get a policy and a plan rather than just doing these online planning. So I think building up a value function to allow you to do shorter horizon planning in your MPC is definitely like an interesting direction. But yeah, I think the hard part of the laundry would be the planning part, not so much the dynamics, if I had to guess. Okay, we got another question. For the key point detection, what's the accuracy you can get? How do you see if this method extends to tasks that require accurate position? For example, you mentioned that the method would fail for smaller mugs. So that project, which was the second one, the one hanging the mugs, that's supervised learning, you can get really good accuracy. So like sub-centimeter accuracy. So the reason we were failing on the smaller mugs is actually not because of the perception system, really. It's because, let's see if I can find a little mug here. Okay, I've got my trusty C-cell mug. So what happens is the real failures are coming from the fact that pipeline's open loop. So you would look at the world, you detect the key points, but now when you go in for the grasp, inevitably in the real world, whenever you grasp something, you actually end up moving it just a little bit when you grasp it. So if you have a mug that has a big handle like this, that's fine. You're still going to succeed at the task. But if you have a handle that's 1 centimeter in diameter and then you move the mug half a centimeter on the grasp, that's where the failure comes from. But I think the solution is just to move to a closed loop. That's not a fundamental limitation of the method. Just move to a closed loop system, reperceive after you grasp, or use a contact sensor for finer localization, and that's solvable. So you can get really accurate detections. Speculation request. Okay, from Eric Cozino. How well do you think this would handle object grasping and re-grasping of an object, like reorienting a mug? How would you do the play to learn the dynamics part? So one thing that maybe an astute observer noticed is that there isn't a natural way right now to handle occlusions. So partial occlusions are sort of fine. As long as the camera can see some of the key points, it's okay. But I think for things like grasping, you're really going to get into heavy occlusion. So I think going to a multi-camera setup or using tactile sensors is actually going to be pretty important. Maybe we can speculate more offline, Eric.
Sweet, thanks. Also, I think Hankai had a question about the key point speed.
Oh, yeah, so does it help? So Hankai's question is, does it help if you include the key point speed into the dynamics model? So yes, so in the interest of time, I didn't have this, or in the interest of sort of keeping the slides clean, I didn't have this in the talk, but X is actually the key point, so the state is actually the key point locations in the current image and actually in the previous image. So by having both of them, you get velocity. I think that hopefully that answers your question. Speculation request from Pete. For new graduate students just starting out, what related or adjacent research problems do you recommend they work on? I think stay in the world of closed loop feedback control. I think that is a very rich world and very promising. And I think integrating, I really do like the dynamics learning approach. So I think figuring out how to do that, but integrating more modalities than just vision, especially for dealing with things like occlusion, I think is really interesting. And also how to go from, actually building a value function to get sort of a global policy rather than just relying on your MPC to get you there. I think those are all fruitful areas. Okay, I think I've answered all the questions from the chat. So if there are other questions, feel free to unmute yourself and just ask.
That's awesome. I not only great presentation, but I just love that you have such a community of people that want to know the details and everything like this. Really, really good. Sorry that we ran over. Sorry to the committee, I guess, who have to stay. Everybody else stayed optionally. Okay, so here's what we're going to do now. I'm going to shuffle the committee for sure into a breakout room. If there's any faculty who would like to join us in the breakout room, you are welcome. Just send me a quick chat right now and I will include you in the breakout room. I'll leave everybody else here. You're happy to talk amongst yourself, discuss the finer points of Lucas's work or whatever you want to talk about. And we'll grow Lucas and then we'll send him back